The third and final application of Gauss law is to find the electric field due to an infinitely large and uniformly charged plane sheet. Again, it's quite a long heading, but I advise you to remember the heading word for word. So what is it? The electric field due to an infinitely large and uniformly charged plane sheet. So let us apply the Gauss law to find this electric field. First of all, the diagram. So let's say you have a large plane sheet. Okay, so let's say that is the plane sheet. Alright, and then on the plane sheet you have the positive charges. Okay, since this plane sheet is uniformly charged, it will have a constant surface charge density. Alright, now the plane sheet is like this. So what will happen? This plane sheet, it will produce electric field in that direction. There will be electric field from all the positive charges. Okay, from all the positive charges there will be electric field in that direction. Okay, and similarly there will be electric field in the backward direction, because there will be charges present in the backward side, in the back side of the plane sheet as well. Okay, so you can see here that the plane sheet is quite thin. There is electric field going towards the right side of the plane sheet and electric field going towards the left side of the plane sheet from behind. Now we want to find the intensity of this electric field due to the plane sheet. Let me redraw the diagram. We clear this off. So again, here you have the plane sheet. This is a large plane sheet, an infinitely large plane sheet. Okay, so what do we do? Let's say we want to find the electric field at this point, at a point P, which is at a distance, let's say at a distance r from the plane sheet. All right, this at a distance r. Okay, so here again, to use the Gauss law, we have to draw the Gaussian surface. Now the question is, what type of a Gaussian surface shall we draw? Here we can draw a cylindrical Gaussian surface. Okay, so what we do, we draw a cylindrical Gaussian surface in this direction, one which is facing the right side. All right, in this direction. Like this, and this is one of the flat portion of the Gaussian surface. Okay, so this Gaussian surface will go on the plane sheet, and then this Gaussian surface, it will go from behind. Also behind, we have to draw the Gaussian surface. Why do we draw the Gaussian surface behind also? Because the electric field is coming out from behind, from the left side of the plane sheet as discussed just now. So again, you have here, that is the flat portion. Alright, so just like before, you will have three regions of the Gaussian surface. You have this one as region 1, this as region 2, that is region 2, and this as region 3. Okay, so what do? We again have to draw, let's say we take a small area out here, a small area. Now since this face, let me use yellow, this face, it is facing that direction, yes or no? It is facing that direction. So therefore the area ds, this area ds, it will be pointing in that direction. Okay, so that is ds bar. Again, what is ds? ds is the area of only this small portion. Let me rub off the yellow part. Okay, so that is ds. Now you remember or not the electric field? Electric field, since this is the plate and the plate has got these positive charges on the plate. So what will happen? The electric field will be coming out, right? It will be coming out like this. So how does the electric field come out? It comes out perpendicularly. Perpendicularly to what? Perpendicularly to the plane surface, to the plate. Okay, so therefore this electric field will be pointing in that direction, E bar. Similarly, what we do on the region 1, we draw a small surface. Now this surface is directed towards the left side, so therefore this will be ds. And again, from here the electric field is coming out in that direction. Okay, electric field, it is going like this in that direction. Alright, so you have the electric field E bar like this. Got it? So that this electric field is making an angle 90 degree with respect to the sheet. Okay, right, so it is very important to note the direction of ds and electric field. In this case here, what is the angle? The angle will be 0 degree. In this case also, since ds and E are pointing in the same direction, the angle will be 0 degree. In region 2, let us draw the area like this, ds. Now this area is facing up. It is facing up like this. This is ds. Okay, and the electric field crossing ds will be in which direction? The electric field will be in that direction. Right, that is E bar. So what is the angle here? Theta here will be 90 degree. Got the idea? So again, let me just explain. We have this sheet out here. On the sheet you have the charges. The charges are, this is the front side, and this is the back side of the sheet. So obviously the charges won't be only on the front side, it will be on the back side also of the sheet, right? But I cannot draw the back side out here, so we are seeing only the front side of the sheet. Now these are the positive charges, they are evenly distributed. Okay, so what will happen? There will be electric field pointing in that direction from all the positive charge in that direction. How does the electric field emerge out of the plate? Perpendicularly with respect to the plate. There will be electric field also in the backward direction like this, perpendicularly from the plate. So to use Gauss law, what we do is we draw the Gaussian surface. What type of Gaussian surface are we drawing here? We draw this cylindrical Gaussian surface. Okay, so let's say we want to find the electric field at this point P. Okay, point P is at a distance r from the plate. So we draw a Gaussian surface, a cylindrical Gaussian surface in such a way that this flat portion, it passes through point P. Do you see the flat portion? So that means the distance of this flat portion from the plate will be r. Similarly, the distance from here till here is r. Okay, right. So on the Gaussian surface, so we draw the Gaussian surface in the front side. In the front side, why? Because we have electric field going in the front side, and we also draw in the back side. We have the electric field going in the back side. Okay. Now again, if since this is a cylinder, you will have three regions: 1, 2, and 3. So just like before, what we do is we take a small area on this region. This area is facing right side, so therefore its area vector ds will be pointing in that direction. This is ds. And what is the electric field passing through this area? Electric field is coming from the plate. It is going through the area and going in the same direction as ds. What is the angle between ds and e? That is 0 degree. So similarly here, we take a small area here ds, and this face, it is facing the left side. So therefore ds will be pointing in that direction. So again, what is the electric field passing through ds? It is coming from the plate and passing through ds along the same line. So the angle between E and ds here also is 0 degree. But if you look at region 2 here, we take a small area out here. So this small area is facing this side. Okay, is facing in that direction, right? And the electric field always comes out from the plate. No, the electric field comes out from the plate like this. Right? So at this point, in which direction the electric field is going? It is going in that direction. Electric field is always perpendicular to the plate. Got it? Now, what is the angle between ETS and E? The angle now is 90 degree. Okay. So let us now apply Gauss law. By Gauss law, you have integration, closed integral E dot ds is equal to q by epsilon naught. Right? So again, just like before, in the first application, what we can do is we can break this integration into three parts. So this will be integration in region 1, E dot ds, plus integration in region 2, E dot ds, plus integration in region 3, E dot ds. This is equal to q by epsilon naught. What do we do next? We apply the A dot B formula. In region 1, you have E ds cos of the angle between E and ds in region 1. Look, what is the angle? 0 degree. Plus, here also, region 2, E ds. Oh, what did I do? E ds cos of the angle between E and ds in region 2, how much? 90 degree. Plus, in region 3, E ds cos, again region 3, the angle is 0 degree. This is equal to q by epsilon naught. Okay, so obviously this will be 0, right? Why? Since cos of 90 is 0 degree. Here cos of 0 is 1, cos of 0 is 1. So you will have only region 1 EDS plus region 3 EDS is equal to q by epsilon naught. E, I can take it out. Region 1 ds plus here also E, region 3 integration of ds is equal to q by epsilon naught. Okay, I want you to look at the diagram. Just have a look at the diagram. So here in region ds in region 1, just look here, in region 1, ds is this. So if you integrate this part in region 1, what will you get? You will get this entire area, isn't it? You will get this entire area, right? So let the area of this face be A. Okay, so here how much you're getting? You will get A plus E. Similarly this one, ds. If you take this and you integrate, you will get this entire area. Isn't this area and this area the same? That also will be A. So here also I'm getting A is equal to Q by epsilon naught. Okay. So how much am I getting here? 2EA Q by epsilon naught. So E is equal to Q by 2 epsilon naught A. What is charge by area? Charge by area, this is equal to sigma, the surface charge density. So therefore you have E is equal to sigma by 2 epsilon naught. This is the required expression. Interestingly, do you see any R out here? Will E depend? Just look at this equation. Call this equation 1. Does E depend on R? Does it depend on the distance? Look at the diagram. Does it depend on the distance? It does not depend on the distance. Okay. So it means that if this plate is an infinitely large plate, the electric field will be constant. It will not be depending on any distance. Alright. You practice this nicely as well. Thank you.